What happens when you combine two of the most powerful and frankly weirdest fields in science? What do you get when you take the bizarre world of quantum physics and you smash it into the creative power of artificial intelligence? Well, let's dive in, because a really clever new idea is giving us a glimpse of what that future might actually look like.
So let me ask you this. Can we really use the strange rules of the quantum world to teach an AI how to do something creative, like generate a new image? It sounds a bit like science fiction, doesn't it? But that's the exact question we're going to explore today. And the answer is surprisingly practical. To really get this, we have to rewind a bit, all the way back to 1982. The legendary physicist Richard Feynman had this kind of radical idea. He said, nature isn't classical, it's quantum mechanical. So if we want to simulate nature, we'd better build a quantum computer. He realized the best way to understand that world was to build a machine that plays by its rules. And that single thought really set the stage for everything we're talking about today. So you fast forward a few decades, and Feynman's idea has blossomed into this incredible field called quantum machine learning, or QML. The promise here is just huge. We're talking about computers that could potentially solve problems that are literally impossible for even our best supercomputers. And, this is a big deal, they could do it using way, way less energy. But, and there's always a but, here's the reality check. The quantum computers we have today are in what's called the NISQ-era. That stands for Noisy Intermediate Scale Quantum. The keyword there is noisy. These machines are incredibly fragile. Think of them like a super sensitive microphone that picks up every tiny vibration. That noise causes a ton of errors in their calculations, and that's been a major roadblock. So what do? Well, some really smart researchers came up with a new approach. Instead of trying to build a perfectly silent room for that microphone, they designed a system that's good at picking out the signal from the noise. It's called a Quantum Reservoir Computer, or a QRC. It's a type of QML built specifically to work on these messy, error-prone machines we have right now. It's almost like it's designed to thrive in a little bit of chaos. And these QRCs have some amazing things going for them. They're super energy efficient and they can handle huge amounts of data. But they have one massive Achilles heel. Their accuracy just isn't there yet. They can get you in the right ballpark, but they can't hit the bullseye. So you've got this incredibly efficient engine that's, well, a bit sloppy. Okay, let's put a pin in that for a second and hop over to the world of classical AI. Because over here, we have this genius tool for getting things super accurate. It's called a Generative Adversarial Network, or a GAN. A GAN is basically an AI that gets smarter by arguing with itself. It has two parts, one that creates things, called the generator, and one that judges them, called the discriminator. The best analogy is a forger and an art detective. The forger, that's our generator, paints a fake Mona Lisa. The detective, our discriminator, has to tell if it's real. In the beginning, the forger is terrible, and the detective spots the fake a mile away. But the forger learns from its mistakes. It tries again, a little better this time. The detective also gets smarter. This back-and-forth competition forces both of them to become world-class experts really, really fast. And this is where the big idea happens. A researcher named Hikaru Wakarara looked at these two pieces of the puzzle. On one hand, this efficient but sloppy quantum tool, the QRC. On the other, this amazing AI training method, the GAN, that's great at forcing accuracy. And he thought, wait a minute, what if we make the sloppy quantum computer the forger? And just like that, the Quantum Reservoir GAN, or QR-GAN, was conceived. And what's so brilliant about this is that it's not a hardware fix, it's a software one. You take the raw, kind of messy creativity of the quantum computer, and you pair it with the sharp, critical feedback of a classical AI. It's like giving our quantum forger a world-class art teacher. Okay, that's an absolutely fantastic idea on paper. But science is full of beautiful ideas that just don't work in the real world. So the number one question is, does this hybrid mashup actually perform any better? Does it really work? To find out, the researchers set up a little competition. In one corner, you have the new hybrid, QR-GAN. They pitted it against a standard, purely quantum GAN and a traditional classical neural network. The task for all of them was pretty simple. Look at a bunch of handwritten zeros, and then try to draw one yourself. And the results? Well, they speak for themselves. After 500 rounds of that forger detective game, the new QRG model produced a zero that was clear, well-defined, and looked a lot like the real thing. That adversarial training process clearly worked. Now, what about its purely quantum rival? The standard QGAN, without that classical detective helping it out, really struggled. The image it produced was blurry, less defined. You can tell it's supposed to be a zero, but it's not nearly as sharp. It shows just how valuable that hybrid feedback loop really is. And here's the kicker. The purely classical network didn't do so great either. In the same amount of time, it couldn't create a coherent image. So this new hybrid wasn't just better than its quantum peer, it actually outperformed the traditional AI approach in this specific task.
Okay, so drawing a zero is one thing, but what about something more complex? The researchers really turned up the difficulty and had the models generate more complex images from a standard dataset. They measured the error, basically how wrong the generated image was. And as you can see, lower is better. QR-GAN consistently had the lowest error rate. It wasn't just a little better, it was significantly more accurate.
So, case closed, right? QR-GAN is more accurate, it's more efficient, it's the perfect solution for quantum AI. Well, in real science, it's never quite that simple. The researchers themselves are very honest about the next set of challenges. For one, can this scale up to create really big, high-resolution images? We don't know yet. And what happens when the data you give it is also noisy? And maybe the biggest hurdle of all, these incredible results were run on a simulation. The final boss battle is getting this to work just as well on actual physical quantum hardware. So when you boil it all down, what's the big takeaway here? Why should you care? Because this is a huge deal. QGRN shows us we don't necessarily have to wait for someone to invent perfect quantum hardware. This is a brilliant software idea that makes the messy, noisy hardware we already have today much more powerful and useful. It's a clever algorithm that's bridging the gap between where we are and where we want to be. A breakthrough like this just blows the doors open. It proves that these hybrid quantum classical systems are a really promising path forward. And it leaves us with this incredible, inspiring question. If we can teach a noisy, imperfect quantum computer how to draw a picture today, what truly complex, world-changing problem are we going to teach it to solve tomorrow?